This video is a summary of the 4 required practicals that can be examined in AQA GCSE Chemistry Paper 2. When it comes to prioritising topics for revision before your final exams, the required practicals should be at the top of the pile because you know that they're worth 15% of all of the marks, and that means they're much more likely to come up than anything else. The first required practical in GCSE Chemistry Paper 2 is about investigating the impact of changing concentration on the rate of reaction. But actually, this is 2 different practical activities. There's one in which we measure the rate by collecting some gas, and that could be either in a gas syringe or collecting it over water. And then there's another investigation where we're examining turbidity, which means cloudiness. So this is the experiment that you might think of as the disappearing cross experiment. Then in Unit 8, which is the chemical analysis topic, there are 2 different required practicals. The first one is paid chromatography, and the second one, which is just for the triple scientists, is ion testing. And this can be split up into flame tests, hydroxide tests, and the tests for carbonate ions, halide ions, and sulfate ions. And then finally, we have the water purification and testing practical, which comes up in Unit 10. Out of those 4 required practicals, the first one is the only one that is a traditional investigation. In other words, we're going to need to change an independent variable, measure or observe or record a dependent variable, and also identify some control variables that we're going to keep the same. So since we're changing the concentration, that's our independent variable, and then we're measuring the rate of reaction, or strictly speaking, we're measuring a time and using that to calculate a rate of reaction. And then we're also going to need to identify some control variables. The first required practical is a classic textbook example of where you might expect the exam board to ask you to write a method. In this question, we're asked about investigating the impact of concentration on the reaction between magnesium and hydrochloric acid. So although the question doesn't make reference to the fact that we're collecting gas, we've got a clue in the state symbols in the question. So we can see here that we've got hydrogen gas being produced, and that tells us that we're interested in collecting gas, not turbidity. So in this investigation, the independent variable is going to be the concentration of the acid. The dependent variable ultimately is going to be rate, but what we're actually measuring is going to be the volume of gas that is produced per second. And it's important that it's per second because if it wasn't, we wouldn't be able to calculate a rate. And then we're also going to need to identify some control variables if we want all 6 marks. So here we're going to control the volume of the hydrochloric acid, and it's really crucial that we don't say amount because that's not true. Just ban the word amount from your vocabulary, you don't need it. We're also going to control the mass of magnesium that we're added, and we could control the temperature, but realistically we're probably not going to. If you're going to talk about controlling the temperature, then you need to be actively doing something to keep it the same, like carrying out your reaction in a water bath. In a typical method, I'm going to start out by describing how I would measure the volume of my acid, and of course, wherever I can, I want to name the equipment, so I'll talk about using a measuring cylinder. The fact that I've put 10 centimetres cubed is not particularly important. You could use 10, you could use 20, but what I'm doing is by naming a volume, I'm saving myself time because it means when I repeat the investigation, I don't need to say and keep the volume the same because I've included the volume within the method. Then I'm going to measure out my half a gram of magnesium. Again, it's not important that it's half a gram, it could be 0.2, it could be 1, but I am going to give my equipment again, so I'm going to say using a balance. And then crucially, you need to make sure that the reaction is actually going to happen. So we're going to talk about simultaneously adding the magnesium to the hydrochloric acid and also starting a stop clock. Here I've needed to talk about putting the bung back in because I'm using a gas syringe as shown in the diagram, and otherwise some of the gas would be lost. If you were asked to write your own method without the picture of the equipment, you might also describe collecting gas over water, which is where you have an upturned measuring cylinder full of water and the gas as it's produced is displacing that water, and therefore you can see the volume of gas that's being collected. My next step is going to be to record the gas that's released each 10 seconds. Again, the 10 seconds itself isn't important. What's important is that you're doing it at regular intervals. And then I'm going to repeat steps 1 to 4 3 times and calculate a mean value. Remember, in GCSE Science, there is never a mark for just saying repeat. It needs to be repeat and calculate a mean, or possibly repeat, remove anomalous data and calculate a mean. Then I'm going to repeat steps 1 to 5 using hydrochloric acid of a different concentration. And I might want to describe that I would produce that different concentration by diluting the acid. Finally, I could describe that I would calculate rate by doing the volume divided by the time, and I could describe that the reaction that produces the most gas per second has the highest rate. Alternatively, I could be given details of a reaction that's going to become turbid. So again, my independent variable is the concentration of the hydrochloric acid, and my dependent variable is effectively the rate. And I can identify that this reaction is going to become turbid because I can see in the symbol equation that sulfur has got a state symbol S after it. So that tells me that a solid is being produced from the solutions, and therefore that precipitate is going to make the reaction become cloudy. So this time I'm going to describe how I would take my different volumes of hydrochloric acid and top them up with water. I could also say that I would take 5 different concentrations of hydrochloric acid, depending on the exact style of the question. Then I'm going to talk about how I would use a separate measuring cylinder to measure out my sodium thiosulfate, because I don't want the reaction to start in the measuring cylinder because those chemicals are effectively mixing. Then I'm going to make sure that that is in either a McCartney bottle or a conical flask. And I'm going to put that over a pencil cross, because remember, the way that this reaction works is that as the precipitate is formed, you lose sight of that cross and it stops being visible. You might describe how you're going to warm them so that they're at a particular temperature, but you only need to do that if you're using that as a control variable. And to be honest, there are enough other control variables in this reaction that I probably can just omit that. Then I'm going to add the acid to the sodium thiosulfate. If you know this reaction well, you know that if we're doing it in this small volume, we only need 1 centimetre cubed of acid. But if you didn't know that and you'd said add 10 to 10, that would be fine as well. Then you're going to time how long it takes for the cross to disappear. And then you're going to talk about repeating that and then repeating it again with the different concentrations of acid. The control variables are important, so you probably want to explicitly say that you're going to keep the concentration of the sodium thiosulfate the same, although we have already described in the method about keeping both of the volumes the same. And then finally, again, we can say that if we compare the times, the shortest time is going to translate to the fastest rate. For the second paper 2 required practical, you should have set up and analysed a paper chromatogram. This is usually comparing a few different felt tip pens to see whether they contain the same mixture of inks. In setting up the required practical, there are some key things to note. Firstly, you need to draw a start line, and it needs to be in pencil because a pen might run and interfere with your results. Whichever solvent you're using for your mobile phase, that needs to start below the pencil line, because if you add too much solvent, then your samples will just run out into the solvent rather than being drawn up the paper. If you're using a volatile solvent such as methanol, then you probably want to put a lid over the top to stop that solvent from evaporating. Chromatography is a comparative method, so that means that in order for us to have any results, we need something to compare our sample to. And so we can put standards, which are known substances, also on the start line so that we can compare them. At the end of your chromatography, you need to say that we're either going to compare your sample to those standards or calculate an RF value. So this would be a really straightforward method to write. We'd start off talking about how you're going to draw a pencil start line, and you might want to include that information about how you don't want the start line to run. Then onto that start line, you're going to put little dots of the known substances, those inks that you're using as standards, and then at the end of the line, you put your actual sample. Then we're going to place the very bottom of the chromatography paper into the solvent, ensuring that the solvent doesn't touch that start line, because otherwise all of our samples would just run out into the solvent rather than going up the paper. Then you're going to leave that chromatogram to have the inks separate out. And then once the solvent front reaches near the top of the paper, you're going to remove the chromatography paper from the solvent and leave it to dry. At this point, you'll be able to qualitatively compare the position of the colours from the sample to the known colours, but also quantitatively, you could calculate RF values for each colour. Strictly speaking, you should also repeat this again using a different solvent, because lots of different substances have different solubility in different solvents. So if we know that 2 substances are appearing in the same place in multiple solvents, that gives us additional evidence that they are actually the same substance. In real life, your chromatogram and your final results might have looked a little bit like this. But in an exam, you'll be analysing a set of results that look more like this. We can start off by looking at the number of spots, which is going to tell us the number of different substances in our sample. And we can also compare the position of those spots to the standards. A pure element or compound will produce a single spot in all solvents. So each of the 6 standards here are pure substances. But my sample contains 3 different substances. And it's probably worth pointing out here that although we do use paper chromatography to separate out colours, and that's a likely context for an exam question, your exam paper is going to be printed in black and white. So when they ask you how many different colours does the sample contain, what they're asking you to do is identify how many different spots there are in that one column. So this sample here contains 3 colours, even though all of the colours on my page are black. Then I'm going to compare those 3 dots to the standards. You can see that I have one dot in my sample that is at the same height as standard B, so that tells me that my sample probably contains standard B, and then there's another dot at the same height as standard A, so that tells me that it also contains standard A, and the top dot doesn't line up with any of my standards, so I have something in my sample that is not any of those standards. To analyse the samples quantitatively, we can use RF values or retention factor values. An RF value is a number that tells you how soluble a particular substance was. It's a fraction where the distance that the substance travels is divided by the distance that the solvent travels. That means it's always going to be between 0 and 1. If the value was 0, that would tell you that that substance was completely insoluble and it would stay on the start line just like standard C is in this diagram. And if the value was 1, that would tell you that that substance was extremely soluble and it had travelled the exact same distance that the solvent had. The next required practical is only for those taking GCSE Chemistry, aka Triple Science, and it's about identifying unknown compounds. You should know that metal compounds produce characteristic coloured flames when they're burned in a Bunsen burner flame. This doesn't produce good results if you have a mixture of ions, as the different colours can obscure each other. Having cleaned the nichrome wire by putting it in a Bunsen burner flame and also in some hydrochloric acid, you can then dip that into a solid salt or a salt solution and then place that wire into the edge of a Bunsen burner flame and observe the colour seen. Another way to identify positive metal ions is by adding sodium hydroxide solution. This causes those metal ions to precipitate out, in other words to produce a solid, and the colour of that solid helps us to identify what the metal might be. So first up, I've got copper, and if I add the sodium hydroxide, you can see it was already blue, but now at the top you can see there's a sort of a blue solid, a blue precipitate being formed, and that is copper hydroxide. And then likewise, this next one is iron 2+ ions, because remember, iron being a transition metal has multiple stable ions. So these are the iron 2+ ions. And they produce this characteristic sort of dark green colour. And then in contrast to that, iron 3+ ions produce a much more orangier colour. So if you think about rust, that's hydrated iron oxide and it's iron 3 oxide. So, you know, this is rusty coloured because that's the colour that we would expect all iron compounds to turn. Now, my last 3 are a little bit harder to tell the difference between because they all form white precipitates. So these are calcium and magnesium and aluminium salts, and you can see they don't look identical to each other, but they are all forming a white precipitate. So that's not hugely useful. It means I can tell that it's one of the 3, but I can't tell which one it is. However, if I add an excess of sodium hydroxide, then aluminium ions will redissolve. So if I have a look at that, still very much precipitate. Still not really seeing any change. But with this last one, it's not very easy to see on the video, but around the sides we can see it starting to redissolve. If I lift the camera up slightly so you can see the top of the tube. The top of the tube is starting to sort of clear out, and that is very much starting to redissolve. If I compare it to the other 2, you can see they're still opaque, they still have precipitate, but my aluminium is separating out. Now, if I wanted to tell the difference between the calcium and the magnesium, there is a way I can do that, and I could use a flame test, because obviously when I put those compounds into the clear part of a Bunsen burner flame, I would be able to see that the calcium compound would give me a nice brick red, orange red flame. So to start with, I'm going to add a little bit of hydrochloric acid to each tube. And now I'm going to add some barium chloride. And the barium chloride, if there are sulfate ions present, then the barium ions will join up with those sulfate ions to make barium sulfate, which is a white insoluble precipitate. So I'm going to see the solution produce this white precipitate and go slightly cloudy. So if I add some to this tube, not a lot happening, no sulfate ions there. But if I add some to this tube, then I can see that white precipitate forming. So again, this is a two-part test. We're going to start out and we add some nitric acid, and the nitric acid is in there to remove other negative ions that could give us a false positive. So we put a little bit of nitric acid into each tube, so any carbonates that are in there will react and disappear. And then to those, we're going to add some silver nitrate. So, for instance, if we have a solution that contains sodium chloride, then the silver ions will react with chloride ions and produce silver chloride, and we're going to see a precipitate. So, a little bit of silver nitrate to each tube. And here they are in order. So the first tube contains sodium chloride, or did contain sodium chloride, and it now has, this is a white silver chloride precipitate. And then my second tube with the cream precipitate, that one is containing bromide ions, so this is a silver bromide precipitate. And finally I've got my iodide ions, so you can see as we go white and then cream and then sort of a pale yellow. To test for carbonate ions, I add acid, and as you can see it bubbles up, and I can pass those bubbles through lime water or aqueous calcium hydroxide, and gradually a white precipitate forms and that solution goes cloudy. There isn't one single method for this practical that you can memorise, because they could give you literally any compound and ask you to identify how you could confirm what it is. But here's just one example. So in this example we're asked about tablets that might contain potassium iodide. So to identify potassium ions we need a flame test, and iodide ions we need the silver nitrate test. So you would talk about the fact that you would place that sample on a nichrome wire, and you might choose to include for some extra detail how you would clean that wire beforehand. And then you would describe how you would hold that in the roaring flame of a Bunsen burner. Although again, the most important thing is just the flame. You could probably get away with not mentioning the roaring bit and the Bunsen burner bit. And you could go on to say that you would observe a lilac flame, and that lilac flame would tell you that the sample did contain potassium ions. Then for your silver nitrate test, this is going to work with a solution, so we need to turn that tablet into a solution by crushing it up and then dissolving it in some distilled water. So then once we've done that in a test tube, we can add some dilute nitric acid to remove any carbonate ions. And then we could talk about how we would do that with a dropping pipette. And then after we've done that, we would add silver nitrate solution. And if the iodide ions were present, we would observe a yellow precipitate, which would tell us they were there. The final required practical in Chemistry Paper 2 comes from Unit 10, and this is for both combined scientists and triple scientists, and it's my least favourite required practical because unlike all of the others, there is absolutely no way that you can write a method and learn it, because this isn't really one investigation, it's just lots of little bits that get put together. So the purpose of this required practical is to identify whether or not a sample of water is pure, and then assuming it's not pure, purify it and then prove that you've managed to do so. There are a bunch of different ways that you can do this, but your starting point is probably to identify whether there is anything dissolved in that water at all. So although we can't see salt, we can identify that it's there because if we evaporate the water, the salt or the minerals will be left behind. So to do this, you would take a watch glass and measure the mass of that beforehand. and then add a sample of water that you've measured the volume of and heat that watch glass, usually over a hot water bath, so you're gently heating it until all of the water is evaporated, and then measure the mass again with a balance to see whether there have been any salt residue left behind on that watch glass. This is quite tricky to do well, firstly because if you heat the watch glass too vigorously then it will just shatter, and secondly because if you don't heat it vigorously enough then some water will be left behind and you'll end up with a higher mass, which would indicate that your water isn't pure. The other thing that you need to watch out for is that because you've been heating it over a water bath, the underside of that watch glass will get wet, and so if you don't dry it off before you measure the mass, again that's going to increase the mass. The second thing that you can do is to use either an indicator or a pH probe to measure the pH of the water. At GCSE, we say that the pH of pure water is going to be exactly 7, so perfectly neutral. Thirdly, you could measure the boiling point. For a pure substance, there is going to be a single, unchanging, sharp boiling point that you can look up in a data book. So for water, this is exactly 100. And if your water is not boiling at 100, then it's not pure water. If you are taking triple science, then this practical could be joined together with the previous one, because we could ask you to identify whether there are any, for instance, sodium ions or chloride ions present by using flame tests or halide tests. But this isn't applicable if you're doing combined science because you're not supposed to have learnt about those tests. Once you've established that a sample of water is not pure, the second bit of the practical is about purifying it. We would do this by distilling it. This means heating the water up until it evaporates and then cooling it down until it condenses. Since anything else that would be dissolved in it, like sodium ions or chloride ions, is going to have a different boiling point, that will be left behind when the water evaporates. The sample of impure water that you want to distill will be placed in either a conical flask or a round bottom flask, with a bung at the top with a delivery tube coming out. That flask will be heated, usually using a Bunsen burner, until the water began to evaporate. As it rises up, it would cool down and potentially pass through a condenser, which I haven't got in this picture here. And then as those vapours condensed, we would have pure water which could be collected on the other side. This could be then tested again to demonstrate that it is now pure. Here's an alternative diagram of some similar apparatus just so that you can see the condenser. The point of that condenser is that it's a glass tube that has a sort of coat of cold water around the outside, and that helps to cool down the vapour so that it does condense and the pure water can be collected at the end. Thanks very much for watching, and I hope you're now feeling a little bit more confident in describing how to do the required practicals for AQA GCSE Chemistry Paper 2. If you did find this useful, then don't forget to like and subscribe for more GCSE Science revision videos coming soon.